Let's resume 3.3 linear regression. All the technical aspects were pretty much covered, and what's left is just theory. Before that, however, just a little bit of review. Here are very important formulae, regression line formulae. When you know the x value and if you want to find out the prediction of y, you use the first formula. If you know the y value and if you want to find out the prediction for x value, you have to use the second formula here. For example, if x is midterm, y is final exam score, and if your midterm exam score is known, plug that value right over here. X bar, y bar, r, sy, sx, all those are known. So run the computation, you're going to get the best point prediction of the final exam score. Vice versa, if you know the final exam score, plug it right over here. And then run the computation, and you're going to get the best point prediction of the midterm score. In other words, you're supposed to have two regression lines. Line number 1, line number 2. Let me show you. Here, blue is forward direction, red is backward direction. Oh, by the way, I'm going to use the same data table that we used before. Hypothetical class, exam 1, exam 2, midterm and final exam scores are here, and then we can create scatter plots and whatnot. And let me show you the regression lines. Mean for exam x bar, mean for exam 2, and y bar, sample standard deviations, things like those. Okay, these are just routine computations. So let's get rid of all those to squeeze everything into a single viewing window. And here we are. The blue line is the first regression line. When you know the x value and when you want to find out y value, you use the blue one. And red one is the other direction. If you know the final exam score and you want to find out x value, the midterm exam score, you have to use the second. And these are two different lines, and they're symmetric with respect to the line of symmetry, kind of like this. And what are their nature? To make a long story short, here they are. The blue line, the forward regression lines, minimize the regression prediction errors for forward direction. And what are those regression prediction errors? They are measured by vertical distances from the point to the regression line. Why? Because given x value, the best point prediction is given as the point on the line. For example, where my mouse is right now. But observed x value may be a little bit different right over here, which means we have a prediction error. That prediction error is given by the difference of x coordinate values, and it can be visualized by the vertical distances. Not the geometrical distance. Geometrical distance will be given by a slanted line from here, kind of go like this, perpendicularly. So that's where you're going to get the shortest distance to the line, but that's not what we are interested in. We are not doing geometry, this is statistics. We are interested in computation error or prediction error. And error is given by the vertical distances because x is fixed, only y is changing. And if you add up all these, then that's going to be sum of all the errors. But excuse me, you cannot simply add up everything, because if you add up, then pluses and minuses will cancel each other out. So that's not good. What you have to do is take the square of all these vertical distances and then add them up. Because we just took the squares, everything became positive. So if you add up, you're going to get the sum of all those squares of errors. And you want to minimize that so that you get error minimizing scheme. And that's what this blue line is working for. Now, look at the red line. It's very similar, except that this time y value is known and x value is predicted by the point on the line. Consequently, we have horizontal distance. For example, for given y value, we can predict x value right over here on this line where my mouse is. And then real observed x value will be right over here. So this distance, the horizontal distance will be the prediction error if you do backward regression. Of course, if you add them all up, then pluses and minuses will cancel each other out. You're going to get 0. That's not good. So what you need is square them all up and then add them up. And that final summary of all those squares will be the sum total of all the errors, all the prediction errors, squares of prediction errors, to be a little bit more precise. And we want to minimize that. And what is the minimizing scheme? Well, it's this regression line that you're looking at. So depending upon which prediction you're doing, are you predicting y when x is known? We have vertical. And are you predicting x when y is known? We have horizontal. Consequently, we have two different schemes. Consequently, we have two different lines. And these two different lines cause what we call regression effect. Well, this program is randomized, so you can run this one many different times, and each time you're gonna get different starting value. Well, okay, let's go from here. And let's begin with x is about 85 something, and then do some regression prediction. According to the first picture, begin from x equals about 85 and go to the regression line, blue line, and then reading the y-coordinate value, you get 68 point something. That is the best point prediction for final exam score. That is the regression prediction. Now, let's go to the second picture, and we start from this 68.74. And then go backward. Do the regression to find out x value. Are we going to come back to 85? Actually, no, because if we go here, let's see, start from here, where my mouse is, go to this line, and then go horizontally to get the y-coordinate value. Now, when we go back, if you go back to the same line and then retrace the arrow, you're going to get the original answer back, but that is not the case. You have to use red regression line this time because we are doing backward, and the blue regression line minimizes vertical distances. Where is that previous picture? Yes, blue one minimizes the vertical distances, and red one minimizes horizontal distances. They have different functions, different usage. So we cannot just start from here, go to the line and go, and then come right back to where you were. When you're coming back, like the second picture, you have to stop at red line and then come back to the x-axis. What do you end up with? 60 point something. In the end, what did you get? 85 point something, and we regressed back to 60 point something. That's where the name regression was inspired. But actually, regression is going toward the average. So if you start from high above the average, it's a regression. But if you start from way below, then you're going to get a progress, as a matter of fact. But either way, it's called regression effect. And those are related to the nature of regression lines. Two different regression lines and their usages. What do they do? The forward regression line minimizes some of the squares of vertical distances, which actually are the regression prediction errors for forward directions. The latter ones, the sum of the square distances of horizontal distances, which are actually the regression prediction errors when y value is known. That's the theory behind the linear regression. By the way, one final comment to our textbook. We have figure 3.17 and figure 3.18. These two pictures are wrong, and by now you would probably understand why. I showed you two regression lines, one flatter than the line of symmetry and the other a little bit stiffer than the line of symmetry, kind of like where is it? Yes, one flatter, one stiffer. But in our textbook, no, looks like we have a line of line of symmetry here. So they're not even regression lines. These two pictures are wildly wrong, and please do not be misled by this. By the way, one more comment. Figure 3.21 and figure 3.22 visualize pretty much the same thing we discussed before. For forward regression lines, we have to minimize the sum of those vertical distances, right? And those are visualized in 3.21 and 3.22. What if we get wrong line? Then, as you can see in 3.23, we get much bigger error. This is this smallest error that you can get, 23.0, and clearly this is bigger error, 149. This is not the kind of thing you want.